Hello everyone. So in this video we're going to do the infinite potential well problem. It is the first time that we're going to actually apply the Schrodinger's equation, and it is very typical in most quantum mechanical classes that the first application be the infinite potential well, because it is the boundary conditions of this problem allows us to solve it exactly, and it's really quick, especially if we do a one-dimensional form of it like we have here, where we're just taking x. To get started, of course, this is the time-independent form of the Schrodinger's equation, and once again, our Schrodinger's equation in its time-independent form is an eigenvalue problem, where we have a y is equal to lambda y, where a is our Hamiltonian, y is our wave function, and lambda is our eigenenergy or eigenvalue, and multiplied by that same wave function. So just recall that this is an eigenvalue problem, and the problem is as follows. V of x is essentially 0 everywhere between two different boundaries. From x equals 0 in this case to x is equal to Lx. We have these two boundaries. And everywhere else where, below 0 and above or greater than Lx, the potential is infinity. And a real-life scenario, or something very similar to it that you can picture here, because I like to picture things, is if we imagine that we have an electron in free space in somewhere in the universe, away from everything else, and you surround it in some insulating box. Right now, just imagine this: there's this box around it, and you're isolating this electron. Right. And this box has a side L. It's a cube, essentially. And we imagine that L is equal to something really small, something like 2 nanometers. Again, whatever this material is made out of, this box, it's highly insulating, and the likelihood that the electron penetrates through it is very, very low. This is very similar to an infinite potential well problem. It's not quite right. It's not quite there, because having an infinite potential is not physical. You can't really do that. However, you can have a potential that's really high, and the solutions to this equation, the Schrodinger's equation, for the infinite potential well would be really close, or fairly close, to the eigenstates and eigenenergies of this electron here. Right? That is to say, if I take some apparatus and I measure the energy of this electron, I would get a value that's very close to the possible eigenenergies of this infinite potential well problem. Right? And so let's get started with this problem and see where we get. So the first thing to note here is I can rewrite this problem here in terms of its boundary conditions. So boundary conditions is essentially a way of defining the problem such that you can find the particular solution to it. So I've rewritten the Schrodinger's equation here with v is equal to 0, because we know that v is going to be 0 everywhere. However, of course, we have v is infinity at these two boundaries, and we can define that by saying that the wave function, we can ensure that that is the case by saying that the wave function is 0 at those boundaries. So this means that it is 0 at those boundaries. And the reason it's 0 is because this wave function simply cannot exist, or the electron, which constitutes this wave function, it cannot exist past these boundaries. Again, and in order for the electron to sort of penetrate through, it needs to have an infinite amount of energy. This is akin to the classical example of actually being stuck in a physical well yourself, or some ball in a physical well. The ball is really not going to get through. So that is that. And these boundary conditions just tell us that, yeah, it's confined. completely and absolutely confined. So rewriting this, if we rewrite this Schrodinger's equation and we take this kinetic energy component and just bring it over to the other side, we get, what is it? Minus, or keep doing that, sorry about that, minus 2me over h bar squared times psi. All right. And if we set k equal to the square root of 2me over h bar squared, we can rewrite this equation here as minus k squared psi of x. So this is nice because this essentially reminds us of the Helmholtz equation. It's exactly the form of the Helmholtz equation here, and we've gone through the general solutions of this. The general solutions of the Helmholtz equation, there are several ways of writing it. You can write it in terms of the sum of exponentials or the sum of sines, but essentially you want to ensure that you can have any given phase with at different amplitudes. You have the sine term and the cosine term, which are 90 degrees of phase of one another, and you can sum the two with different weights and effectively arrive at any wave, effectively any wave that has one particular frequency. So this, just to recall, is the general solution of this is a times sine of kx plus b times the cosine of kx. Right. So this is one form of writing this general solution. You could also write it in terms of e to the I kx, but we're not going to, due to the boundary conditions in question here, it makes this problem more simpler, essentially, if we write it in this form. But I could have used the exponentials and still arrive at the same answer. So if we applied the boundary conditions, right, we said that psi of x is equal to 0 was equal to 0. If we apply these boundary conditions, we have a times the sine of 0 plus b times the cosine of 0. And this gives us, this is 0, this goes to 0, and this cosine goes to 1. So we are left with just b. So b is equal to 0. That's the first step. And so we're close. The next step is to apply the other boundary, which is x is equal to lx. This is once again equal to 0, which is equal to a times the sine of klx, right, klx, plus b times the cosine of klx. And this, of course, all goes to 0 because we said b is equal to 0. So we're only left with this. Right? And so the question remains, what does this argument need to be in order to satisfy this condition? Right? This argument, of course, if we recall our unit circle, whenever the argument of the sine is either equal to 0 or pi or 2 pi or 3 pi, etc., etc., our sine is going to be equal to 0. So k of x, klx, sorry, if it is equal to 0 or pi or 2 pi we're going to get sine of klx equals 0. And so you can rewrite this as n times pi, where n is equal to 0, 1, 2, all the way up to infinity. And so this essentially tells us that given these boundary conditions and this equation, this differential equation, we have an infinite amount of possible particular solutions, right? And it is defined by these. And so I like to write this as, what is this? Sine or psi of n is equal to, of x is equal to a times the sine of kx, right? We're getting this function up here. B we said was equal to 0, so that doesn't exist anymore. And k, if we solve for k here, and we add a subscript n here, because n can be, it's essentially an argument now, is equal to n pi over Lx. Right? And so if we substitute that in, and there's a little n here now, if we substitute that in, we have a times the sine of n pi x over Lx. And this here is all the possible wave functions of our problem. And of course, we said kn was equal to 2me over h bar squared. And so solving for this, we have E is equal to kn squared times h bar squared over 2m, which I like to just, we often just write a subscript n for the energy, because once again we have an infinite amount of wave vectors, which means we have an infinite amount of these eigenenergies here given by n, and substituting kn for this gives us h bar squared over 2m parentheses n pi over Lx squared. And so here I have written the eigenenergies of our problem, or the eigenvalues of our problem, and the eigenstates or eigenfunctions of our problem for the infinite potential well problem. And so whatever n is gives us a particular eigenstate with the corresponding eigenenergy. And that looks as follows. So here what I have drawn here is I've kind of like superimposed the wave function with this potential well. And so you can see that for the first eigenstate, psi 1 of x, we have this wave form here, right? So if n is equal to 1, which it is for this case, n is equal to 1, we have a times the sine of pi x over Lx, which makes a lot of sense, right? If x is equal to 0, you have sine of 0, which is equal to 0. And if x is equal to Lx, these Lx's cancel out, and we have sine of pi, which is also equal to 0, right? And so these dotted lines, just to be clear, these dotted lines correspond to the point at which psi is equal to 0, right? These dotted lines are psi is equal to 0. Just wanted to be clear here. Don't get confused by the fact that I'm superimposing the wave function onto this potential landscape. So this essentially does mean that at the middle of the well, for the psi equals 2, or the psi 2, or the second eigenstate is equal to 0 as well. So here the wave function is supposed to cross the origin, and this effectively means that the probability of finding an electron in the middle of the well, assuming that the electron is in its second eigenstate, is precisely 0, right? So that's what this wave function tells us. And so I hope this makes sense. You can recall using the de Born's hypothesis, or not de Born, but just Born's hypothesis, or Born's postulate, that what is actually meaningful and what is physical isn't the wave function itself, but the square of the wave function. So we have to recall that the probability density is proportional to the wave function squared. Right, so we have to square these in order to get something that is of actual utility. So let me just give you an example as to how that would look like. Once again, this is infinity, and we take our, let's say we take our second eigenstate. So this is psi 2 squared, right? This is the second eigenenergy. This would look something like this. Roughly speaking, right? I know I'm not doing the best job at drawing this, but you get what I mean. And so at the origin, the probability of finding the electron is 0. And the probability of finding the electron in either this side of the well, the left side of the well, or the right side of the well is precisely 1/2, right? And so if this is Lx, we can say that the probability of finding the electron between 0 and Lx over 2, somewhere in the middle, or right at the middle, is equal to 0.5. And the probability of finding the electron between Lx over 2 and Lx is, of course, 0.5. Right, so this tells us, this gives us the probability distribution. And integrating under this curve, of course, should equal 1, because the electron has to be somewhere. And so I hope all of this makes sense, guys. I will move on from this. In the next problem, I'm going to talk you through a finite potential well, where we actually have a well that is finite in height. So it would look something like this, or by height I mean the potential step would be finite. And so I would have an actual V naught or V0 that is not infinite, and there are also eigenvalues corresponding that can be solved exactly with a finite height. It takes a bit more steps. It's a bit more rigorous, but not so much more rigorous. And I hope that this infinite potential well problem really gives you all the prerequisites necessary, and I'm sure that is the case, in order to solve for this problem. So I'll see you guys in the next video, and until next time.